Hi everybody. We are on lesson 5 of module 3. In the first part of this module we've been talking about dilations. We learned what a dilation was. We've done some experimenting with dilations and we discovered the fundamental theorem of similarity, which is what is referred to in the title of this lesson, FTS. So let's go back to the lesson summary from lesson 4 here and kind of restate our theorem that we experimentally verified and that is stated here. So if we have a dilation with center O and scale factor R, if we pick any 2 points that are in the plane but not collinear, so these aren't in the same line, then the lines, the segments PQ and P prime Q prime, where P prime is the dilation of P and Q prime is the dilation of Q, those segments will be parallel, and they'll also be in proportion with the same scale factor that we dilated the original points with. So this became kind of a surprising result, because we would start from a center O and dilate a point P out to P prime, do the same thing with Q and Q prime with the same scale factor, and they had these properties of being parallel. And whereas these segments on the side we dilated according to our scale factor directly, so we expected them to be in proportion, what we found was that these segments joining any 2 points that we then dilate are also in proportion. So that was kind of a surprising thing to have come up. So what we want to do in lesson 5 is we're going to talk about sort of what happens to this theorem if we turn it around backwards. Okay, so here's the short form of that theorem. If we have this dilation, and it has all these things, the center and scale factor and stuff, if we have the dilation, then we have these parallel lines or segments, and we have P prime Q prime in proportion to PQ by our scale factor R. Okay, so that's our original FTS. That's what it says. What we want to talk about is what's called the converse of that, and it looks like this. Okay, so the converse would be if we have 2 segments, PQ and P prime Q prime, and they're parallel, and they're related by a scale factor, then we have a dilation, and we can find a center for that dilation. So it's going to have a center and a scale factor and all the things that a dilation has. Okay, so we'll see it. We're going to see an example of that right now. But I do want to point out that just because we have this, if we have a dilation, then these things are true. We can't always turn statements like that around. So let's quickly, before we go to exercise 1, which we will in just a minute, let's think about some examples of if-then statements. So consider this statement. If it is raining, then the ground is wet. That seems reasonable. The ground gets wet when it's raining. But can we turn this one around? What happens when we turn this statement around? We have if the ground is wet, then it is raining. Okay, so what we did was we took the if part of our statement and made it the then, and we took the then and made it the if. And if you think about it, this doesn't work, does it? This one here. That's the converse of this statement. If it is raining, then the ground is wet. If the ground is wet, then it is raining. Well, not necessarily. What if we were watering and, you know, the sprinkler hit the sidewalk or hit the grass or whatever? The ground would be wet, but it wouldn't be raining. So you can't always assume that a converse is true. It just depends on the type of statement. If I had a different type of statement, something like this, if the faucet is on, then the water is running. I can turn that one around and say, if the water is running, then I know the faucet is on. So this one works to turn around. The other one didn't, okay? So what we want to do in this lesson is to show that it works to turn the fundamental theorem of similarity around, because we can use it both ways. Then it works for us in more situations. Okay, so we're going to look at the fundamental theorem of similarity sort of backwards. So what we have here are two segments, PQ and P prime Q prime, and they are parallel. And there's numbers on here, 5 and 10, which these don't actually measure out to, again, because of the copying. But we're gonna measure them. We're gonna use our own measurements on there to verify the scale factor. So why don't you go ahead and do that now? Why don't you measure P prime Q prime? It's not 10, and PQ is not 5. So let's put our own measurements on there. And go ahead and do that and turn the video back on. Okay, so by my measurements, I get 8.6 centimeters for the longer segment, P prime, Q prime, and 4.3 for PQ. So the scale factor R, we're asked to determine. I'm going to write it up here because I don't have room. Remember, we said that it's the dilated length over the original length. And so we'll go ahead and do that. 8.6 over 4.3, which is a scale factor of 2. Okay, so if these are really dilated points, then we should be able to find some center of dilation that will work for these segments. And so let's see how we could, I want you to think about how you could find the center of dilation. Based on the lessons that we've done in the past, you should have an idea of what to do to find where O is. And then we'll be measuring some segments to verify the scale factor again. All right, so what you want to do is draw lines like this through P prime and P and extending beyond it, and then through Q and Q prime. And where they intersect, we've kind of worked our way back to our center of dilation. The pen doesn't want to write for me. Sorry. There we go. Center of dilation, O, is where those lines are going to intersect. So what I'd like you to do now is measure, this is the second part of this, measure segments OP prime, so it's this one, and then OP to verify that OP prime, if the scale factor is 2, OP prime should be twice as big as OP, and OQ prime should be twice as big as OQ. So go ahead and verify those measurements on your drawing. Okay, so here are two my measurements for OP prime and OP, 5.7 centimeters, both of these are centimeters, and 2.8 centimeters. So 2 times OP, the scale factor times this one, would be 2 times 2.8 or 5.6 centimeters, which is very close to 5.7. So that's not too far off. For OQ prime, I got 7.3. And your measurement should be very similar to these. And for OQ, I got 3.7. We could get some error in depending on exactly where you drew the line or how you did it. So 2 times 3.7 should equal my 7.3, and it looks like it is 7.4. So once again, I verified the scale factor. So what happened here is we started with segments. We just started with the segments that were in proportion to each other by a scale factor of 2, and we created the dilation that went with them. Okay, so we didn't start with the dilation, we started with the segments, we created the dilation. So we've basically verified that the converse of the fundamental theorem of similarity is true. Okay, you can just watch this example. If you have some graph paper and want to draw it, that's fine too. So we have a line going up here with a point A marked on it. We've got the origin here. That's going to be, we're going to do some dilations here. So we're going to use the fundamental theorem and its converse and practice using them to find coordinates of points of dilations. Okay, so we're going to begin real simply. So here we go. So we have point A and our center of rotation at the origin, or center of dilation at the origin. We're going to make use of our grid lines here to create some parallel lines so that because we know when we have parallel lines, we have a dilation. And so I'm going to drop a line right here down to the x-axis. This is x and y. So I'm going to drop that line down, and I can actually use the x-axis for another ray in my dilation right here. So there's another ray. So we are going to call this point, point B, right here. Okay, so I have a segment joining A and B. We're going to use a scale factor R equals 2 for this example. And so I want to find A prime and B prime. Okay, so this line is slanting up. I could use a compass to mark off some equal segments here, but I'm going to use something a little easier. I'm going to use these parallel lines. So if I use the scale factor on point B along the x-axis, I've got 1, 2, 3, 4, 5. OB is 5. So using a scale factor of 2, 2 times 5 would be 10. So I know that my B prime is going to be at 10. So there's 6, 7, 8, 9, 10 right here. And I can label B prime. And there's my B. And so if this is going to be a dilation, then segments joining A and B and A prime and B prime are going to be parallel. And so I can just draw that segment from B prime up to the line, and there will be my coordinates for A prime. Okay, and so the coordinates of A, let's look at them, are 5 on the x-axis, 2 on the y-axis, and my coordinates for A prime are 10 on the x-axis and 4 on the y-axis. So let's look just by following that, our segments AB and A prime B prime in proportion. In other words, is segment A prime B prime, the length of that equal to 2 times the length of AB. Okay, because we doubled the segment down here on the x-axis, this one, but if this is a dilation, then these segments should be in proportion too. So A prime B prime has a length of 1, 2, 3, 4, which is 2 times the length of AB, which is just 2 right here, 2 units. So 4 equals 4. So that checks out. Those segments are in proportion to one another. Okay, so even though everything's checking out, we should ask ourselves, could A prime have been at any other location? Well, if you think about it, anywhere else we put it, you know, if I put it up here somewhere, then it would not be in the same line with O and A, because this line right here is going to contain the dilation of A, right? And if I put it on the line, but maybe down a little bit over here, say, and drew, because I know that B prime has to be right here, because it's double the distance of OB. But if I drew that, then I would not have parallel, this and this would not be parallel segments, and so it would not be a dilation. So that can't be where my line is. So the only place it can be is straight up from B prime on the line, and that gives us the coordinates 10, 4. Okay, so find exercise 2 in your handouts, and you have this diagram where point A is marked at coordinates 3, 3, right here. The coordinates of this point are 3, 3. And it says, in the diagram below, you're given center O and ray OA. Point A is dilated by a scale factor R equal 4. Use what you know about the fundamental theorem of similarity to find the location of A prime. So again, instead of using a compass or a ruler to do this dilation, we want to use the fundamental theorem of similarity to do that dilation. Okay, so do it just like the example. Come back, pause and come back, and we'll do it together. Okay, so to use the fundamental theorem, I'm going to make use of these grid lines. I dropped a line straight down from A, and I'm going to call that point B. It's going to hit the x-axis right at 3, and the x-axis is going to be my other ray coming out from our center of dilation, O. So since I'm using a scale factor of 4, this distance from O to B is 3, so O to B prime should be 12. So I can just come out here and mark it at 12 on the x-axis. So that's my B prime. So once again, if this is point A right here, the segments AB and A prime B prime have to be parallel to be part of a dilation. So I can just draw the parallel line, and where it crosses this ray that contains O and A, I'll make it purple, this one coming up here, where those two cross is where A prime is going to be found. So this point here is A prime. So the coordinates of that point are 12, 12. Okay, and I found the first 12 down here by just dilating OB by a scale factor of 4. And I found that the y coordinate of 12 by bringing this line up to this ray containing, the purple ray containing O and A. Okay, so I found the location of point A prime. Okay, let's move on. Okay, we're going to do another example before our next exercise. And you can do this one with me or just watch. Okay, so I have drawn a grid and I have point A, which is located at, point A's coordinates are 7, 6. So I've got 1, 2, 3, 4. Let me label my 6, 7, 8, 9, 10. So 5, 6, 7, yeah. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right up at the top. So there's our point A, and we are given this a scale factor. I'll record it right up here of R equals 11 sevenths. Okay, so my scale factor is bigger than 1, so that means my dilated point should be further away from the origin. And it's between 1 and 2, so it's not going to be quite double, right? So looking at the value of that fraction. So what I want to do first is draw my ray through O and A. Okay, so there's my ray going through the origin and my point. And now let's pick a different color. We're going to do what we did before. We're going to make use of our grid lines. I could draw these lines anywhere, but the grid lines are helping me get parallel lines, which helps me use the fundamental theorem of similarity. So if I drop a grid line down and name this point on the x-axis B, then I can use my scale factor to find B prime. So I know that O B prime is going to be the scale factor of 11 sevenths times the distance OB. Okay, so OB prime is 11 sevenths times 7, which is just equal to 11. Okay, so the distance OB prime is 11, so I can come over here and mark B prime. Okay, now this problem has been designed so the numbers come out nicely, at least for this part of it, but it doesn't have to. And you could use a calculator and estimate where your points go to be sure about that. Okay, so so if this is a dilation, then segment AB is going to be parallel to A prime B prime, or dilated A, dilated B. So where this crosses my line up here must be my A prime right there. Okay, so it is, if I look over on the y-axis, that's lining up with a little bit more than 9. So A prime, the y-coordinate of A prime is, the x-coordinate is 11, and the y-coordinate is 9 something. So we could probably mathematically figure out what the y-coordinate is. Okay, so since I have a dilation here, I know that the length of A prime B prime, so I'm going to write this equation right in the middle of my diagram here. So the length of A prime B prime is going to be the scale factor, which is 11/7, times the length of AB. Okay, so the length of A prime, B prime is equal to 11/7 times what? Okay, the length of AB is this length right here, which is 1, 2, 3, 4, 5, 6, because it's the y coordinate of my point A. So this is 11/7 times 6. So this length is 66/7, which if we do the division on that, we get 9.4. We can round it off to tenths there. It's 9.42. So, and that looks reasonable on our graph as well. It's a little less than 9.5. So the coordinates of our point, A prime, which is what we were trying to find, are 11, 9.4. Okay, now you're going to do an example similar to this. So find exercise 3 in your notes. And it says, in the diagram below, you are given center O and ray OA. Point A is dilated by a scale factor of R equals 5/12. Use what you know about the fundamental theorem of similarity to find the location of point A prime. Okay, so work on that and then come back and I will help you out with my results here. Okay, so the first thing I'm going to do is I'm going to use the x-axis as one of my rays that I've dilated out. And so I'm going to drop a line straight down on one of the grid lines. We'll call it point B. And it is hitting at 12, 0. The coordinates of A are 12, 8. Those are the coordinates of point A right there. So we have this, and so again, we always have this relationship of the distance of any dilated segment. So we've got O here. So O B prime. So what I'm trying to do right now is find out where B prime would go on the x-axis. So OB prime, the distance, is equal to the scale factor R times the distance OB, so times the original distance. So my distance OB prime is equal to, I know that R is 5/12, and that the distance of OB, the distance between O and B, is 12. 5/12 times 12. So distance OB prime equals 5. 5/12 times 12 equals 5. So here's my B prime right here at the point at 0.5. I mean at 5, 0. Okay, so once I have B prime, this is very similar to the last example. It's just with a scale factor less than 1. So we're shrinking in towards our center of dilation. Okay, so I'm gonna take this line up to the other ray, and so this must be my location of A prime right here, right on that. Once again, because segments AB and A prime B prime have to be parallel, because we're assuming we have a dilation, and we found the location of B prime, so that tells us where the location of A prime is. But it's not on a grid line, so once again, I can calculate I know the x coordinate of my A prime. The x coordinate is going to be 5. The y coordinate is not on a grid line, so I'm going to calculate it. So we know that the y coordinate will be the length of a prime b prime. So I know that the length of a prime b prime is my scale factor of 5/12 times the length of AB. Okay, so what is the length of AB? So this is 5/12 times this length, AB. So that's the y coordinate of my point A. So that's 8. So 5/12 times 8, which is, let's see, we can do some simplification here. I got 2 and a 3. So this becomes 10 thirds, which is 3.333, repeating. So let's check and by our graph and see if that makes sense. Our y coordinate is just a little bit above 3 on our graph, so it's 1, 2, 3, and a little bit, 3.3. So I can put in my y coordinate over here of approximately 3.3. Okay, last example. This one's a little bit more complicated because we have 2 points already designated here that we're going to dilate. So in this problem, points A and B lie on these rays OA and OB. We have a scale factor of, let me get my pen. Our scale factor is 5/8. So I'll put it up here. R equals 5/8. And we want to find the exact locations of A prime and B prime. So we're going to start like we did before. And again, you can draw this on graph paper, pause it and get up to speed, or you can just watch me do this example. I'm going to make use of my grid lines. So I'm going to draw a segment all the way down to the x-axis there. And I'm going to label the point where it crosses the x-axis. We're going to give that point a name too. We're going to call it C. Okay, so if we want to find the location of A prime, first what we're going to do is we're thinking of this as a third ray coming out, ray OC. I want to find the location of C prime. So if my scale factor is 5/8 right here, remember the scale factor is equal to the dilated length. And this is just another way of thinking of it, right? The dilated length, and we talked about this in class on Monday, over the original length before it was dilated. Original length, okay? So my length OC is 8 right here along the x-axis. And so if that's my original length, 8 on the bottom here, then my dilated length is 5. So I know that C prime, we'll go ahead and erase our coordinate there so I can label it. C prime is right here at a distance of 5 from the center. 1, 2, 3, 4, 5 from the center. So, oops, grab my eraser. All right, so we've got C prime. So we can find the location of A prime by, again, bringing this up to my ray OA. So, because A prime has to lay on that ray. So I know that the x coordinate of A prime is going to be 5, and I'll have to do a little bit of math to find the y coordinate. Okay. So let's go ahead and do that. So length of, so we know we've got these two segments here in red. So my dilated length, which is going to be my y coordinate right here, right? That's following over my y coordinate for a prime c prime, is going to be, so length a prime c prime is equal to my scale factor of 5/8 times length of my original segment, which is AC. Okay, and so the length of AC is 9 because it's the y coordinate of this segment AC. So I can substitute 9 for AC. This is 5/8 times 9. So it's equal to 45/8, which is approximately, approximately 5.6. So look here, yep, it's a little more than 5.5, so 5.6. So my graph checks out with my math right here, which is always exciting. So we'll put in 5.6 for the coordinates of A prime. Okay, so now we want to also find the location of B prime. And by the same token, we've dropped this line down from B at the same time as we dropped it down from A. So my B prime is also going to have a coordinate of 5. This is B prime here. X coordinate of 5, and the Y coordinate is in proportion to segment BC. So we'll do it over here. So B prime C prime length is equal to my scale factor 5/8 times length of BC. Length of BC is right here, and it is the y coordinate there, it's 4. Okay, so I can substitute 4 for BC. Okay, times 4. Let's get some common factors going here. So BC is 5/2, or 2.5. And you can see that right here on the diagram, that this is crossing the line right at 2.5. Okay, so what we've done in this lesson is we've used lots of tools. We've used the fact that we can create these parallel segments on our grid paper, which is really handy for finding the location of dilated points. And in this case, we had to find 2, and so yeah, anyway, so that's what we've done. And so we've used the fundamental theorem of similarity forwards and backwards. So before you go on to the problem set, you might want to read the lesson summary that states the converse of the fundamental theorem, and talks about how we've used it to find coordinates of dilated points.